Okay, so today we're going to continue talking about handle attachments. And what I'd like to do today is to explain some operations that we can do with handles, especially to simplify the realm of all possibilities. So that in particular, we can more easily classify surfaces and kind of understand how to construct 3 and 4 manifolds. So that's the goal. So I guess the idea is how we can basically change the handle decomposition to simplify it, or first how we can change. And I mean, I guess there are 2 things when we think about handle decomposition. So well, basically, if say X is a manifold, a compact manifold, and again, either you assume it has no boundary, or if it has a boundary, we require the function, the Morse function, to be nice. So we pick a Morse function on it. And what I didn't quite say last time, but it was kind of implicit, but we usually want to fix a gradient-like vector field. Gradient-like vector field. And kind of last time, I used the gradient-like vector fields here and there, but I didn't fix one gradient-like vector field once and for all. But let's see how, in the presence of a chosen Morse function in a gradient-like vector field, we can obtain a handle decomposition of your manifold. And I will always assume, I guess I'm going to write it like this, with the usual assumptions. I don't want to write them down again, but I will say what they are. Basically, we want the Morse function to have a unique critical point for each critical value. And I want that, if the manifold has boundary, then, the maximum is attained exactly on the boundary. So basically, it just means if it has boundary, you don't have to worry about the boundary, because, basically, after you go through the last critical value, then you get the boundary of the manifold, and, up to a diffeomorphism, you can kind of stop anywhere after the last critical value. So, it's really whether it has boundary or not, it's just whether you're going to have a last kind of top-dimensional handle to close it off or not. Okay, so I don't want to we don't need to really worry about that. But anyway, so how do we reconstruct the manifold? So we obtain a handle decomposition basically as follows. So, what is a handle decomposition? You can think of it as the following way. So basically, there exists a sequence of manifolds, a sequence of submanifolds. So x0 contained in x1, contained in etc., contained in xm, which is all of x, where xi plus 1 is obtained from xi by a handle attachment. So, basically, how do we get these manifolds? So, we basically take all the critical points and we order them by the critical values. So, how do we obtain these guys? So, how do we? So, what are these manifolds? What are these xi's? So basically, we fix the critical points. So we say the critical points of f are p1 through pm, and such that f of p1 is less of f of p2, is less than f of pm. And we define these to be A1, A2, no, sorry, I don't want to call these A1, A2. Okay, so we order the critical values. I'm not going to actually give them a name right now. What I want to say is I want to choose critical regular values in between them. And the pre-image, everything that's below a certain regular value is going to be one of these manifolds. So now I fix a set A1 through AM. Actually, I think I'll start with A0, A1 through AM. So these are real numbers. These are regular values of f, such that basically they're going to be in between the critical values. Okay? I mean, I guess just because they're in between, that already implies they're regular values, because those are the only critical values. So I want A0 to be less than f of P1, and then less than A1, then less than f of P2, etc., and then less than f of Pm, less than Am. Okay, and then we just define, so we just let xi be the pre-image of minus infinity ai. Okay, I mean, this is just kind of, I'm just solidifying what we did last time. Okay, kind of explaining it and not talking so much about, choosing the regular values. Because last time what we did is kind of, we said, if you don't have any regular values, then you just have a diffeomorphism as you move along. And so I went from like the critical value plus epsilon all the way to the other critical value minus epsilon, and said there's a diffeomorphism there. So I want to do something slightly different today. I just kind of want to break it, just break it in the middle, or somewhere in the middle. And I want to think about the whole thing, from sort of A1 all the way to A2 as just one handle attachment. It's kind of the same thing, but instead of just looking at a little neighborhood of the critical value, I want to kind of just break it up in these like finite number of steps. And up to the diffeomorphism is going to be the same thing. But you'll see why I'm interested in this, because I will actually want to do something a little bit more global and potentially change the critical points around. And so that's why I don't want to just look in the little neighborhood of the critical point. Okay? But anyway, so this is what happens. And the point is, basically, what we showed last time is that xi plus 1 is basically can be obtained from xi via a handle attachment. And what is this handle attachment? So basically, if you have your xi here, so your xi is a manifold with boundary. And then you have your point here, which is your, I guess, pi plus 1. So this is pi plus 1. And this corresponds to the level ai. No, this corresponds to the level f of pi plus 1. I didn't give it a name. But anyway, last time I said, kind of, we first go all the way to this f of pi plus 1 minus epsilon. But how do we get this diffeomorphism? We just use the flow of the gradient-like vector field. So actually, there's really nothing going on here. So I can just look at everything, kind of. So what happened here is that in the neighborhood of this guy, we had this handle. And what was the handle? You could think of the handle as just a product of a ball of dimension k. So if the index of pi plus 1 was k, this was a ball of dimension k times a ball of n minus k. And I'm going to kind of not really smoothen the corner first. Then we can kind of smoothen the corners. But at first, if you don't smoothen the corners, you can think of, there's this guy here. And the picture that I had was kind of like this. I'm going to draw the ball slightly, kind of like this. And then remember, this part here on the left was the pre-image of, I guess, f of pi minus epsilon. And then this part here was f inverse of f of pi plus 1 plus epsilon. And what happened was, if here was your critical point pi plus 1, we looked at we kind of looked at the gradient vector field there. And the gradient vector field, what it does is it does this. So kind of the gradient. So what we said is, okay, we look at a Morse chart and look, with the Riemannian metric that's flat there. So the gradient vector field is just kind of the gradient of that function in the Morse chart. So kind of the gradient vector field here in this little neighborhood was just sort of minus x1 minus xk, and then plus xk plus 1 plus xn. So you could, for example, choose your gradient-like vector field to be this. But anyway, like when you leave this neighborhood, then you don't even have this form anymore. But what's happening is, like, after you leave this neighborhood, you can use your gradient-like vector field, and basically, this line, you're still gonna have this guy. And what is this guy? This is the set of points that are being taken to the pi plus 1 by the flow. So you're going to have some, and it's actually a manifold of points like this. And what is this manifold? This manifold here is kind of very important because it corresponds to, this guy here. So this is called the unstable manifold of the point pi plus 1. So let me define this, because it's kind of important. So I'm going to define the unstable manifold of pi plus 1 to be this set of points in X such that the limit of the flow as t goes to plus infinity is equal to pi plus 1. Where phi t is the flow of the gradient-like vector field. Okay? So this is the unstable manifold, and the stable manifold is going to be the same thing. I mean, this is for every, well, let me just say pi. I mean, this is for every I. So this is the set of x in X such that the limit st goes to minus infinity of the flow is pi. Okay? So sort of the unstable manifold is what's below, and the stable manifold is what's above. And the reason it's called unstable and stable is because usually we think about the negative of this guy, and what's unstable just kind of goes away, and what's stable kind of concentrates. But I don't want to change the signs here in this class. But anyway, what's so important about this unstable manifold, what's kind of important about it is that when you think about the way that the handle is attaching, actually, first one thing, you can see that what is the set here as a manifold? So, it's actually not very hard, so this is an exercise, I guess. And the exercise is to show that, this W of pi and these WS's, so these are smooth manifolds or smooth submanifolds. Which are diffeomorphic to disks, which are diffeomorphic to disks. So the BK, or balls, I guess. It's the same thing, a disk and a ball. It's just a different name. Balls, BK and B index of pi, and Bn minus index of pi, respectively. Okay? And it's not very hard to see that. Basically, you just, in a little neighborhood, in a little Morse, in a little, Morse neighborhood of the point, if your gradient-like vector field has this description, then it's kind of obvious because, the direction that the unstable manifold is just really the RK, the first RK. Because the flow is just e to the minus t here and then e to the t here. So if any of these coordinates are non-zero, then you go away from that point. So you have to be sort of in RK to be converging over there. So in the little ball, you really have, exactly the picture that I drew for you last time. Kind of over here, you go out. No, sorry, over here, you go in. So in RK, you go in. In Rn minus k, you go out. And over here, sort of, if you're not on this RK, then the other coordinate always goes out. So you cannot converge. So anyway, locally, in a little neighborhood, you can see this behavior. But then, by just using the flow of V, you just get diffeomorphism. So you get balls that are, kind of bigger and bigger. And the other thing you can see, moreover, this WU PI is transverse to any regular value that's below PI. So in particular, it's at least before the next critical value. So it's actually transverse to AI. So AI comes before. No. So AI minus 1, sorry. AI minus 1. And WS of PI is transverse to, well, I'm going to say something else, to AI. And the intersection is just a sphere. So, and the intersection with this guy, with AI minus 1, is just a sphere of dimension, index of PI minus 1. And the intersection here is the sphere over here. So, and the intersection of WS of PI with AI is a sphere of dimension n minus index of PI minus 1. Okay, and again, you can see this like locally in a little neighborhood. If you take this guy and you intersect with the value of the function with the critical value minus epsilon, you just get a little sphere here. You can see this explicitly in just in the local form. And as you move this away, it's just a diffeomorphism. So you can just use the flow of V to get this diffeomorphism. So you really just get a sphere here, and you get a sphere over here. Of the right dimensions, of course. Okay, is this clear? So we can see this, in terms of the handle attachment. So basically, if now you kind of move away from the critical point, you don't have the Morse chart anymore. But you still have this picture. You still have this unstable manifold that's converging to this point here. And what is the handle attachment? Basically, what you're doing is you're looking at this unstable manifold, which I'm representing like this, and you're thickening it a little bit. So you have this handle, and it'll intersect. If this is my level AI, it will glue to the boundary of the manifold Xi exactly at a sphere. So I have the sphere S k minus 1. And then I have to thicken it a little bit, and I can actually do a very, very little thickening. And I can glue my handle. Like this. And the point is that the manifold xi plus 1 is obtained from xi exactly via this. So what is this exactly? So what is this handle attachment? I can kind of describe here. And basically the handle attachment is the following. So you take a map, an embedding of s k minus 1 times a b n minus k inside of the boundary of xi. And you can think of this as really, you can think of this actually as first an embedding of the sphere, and then you take a framing of this embedding, which means you look at the normal bundle of the embedded image here, and that will have, if that's framed, that means you can actually find an embedding of this times a ball, a little Rn minus k, or a little ball. So you can kind of think of, you take an embedding of a sphere, and then you take a framing, which doesn't always exist. So you really have to take a framed embedding. Or if you don't want to think about framings, you can just kind of directly embed sk-1 times a ball. But I do think it's more instructive to think about first embedding the sphere and then thickening the embedding. Okay? So you do this, and then now you just kind of take xi union with your handle, and you quotient by the map phi. So you quotient by x goes to phi of x. So this will be your new, so this is your xi plus 1. And there is the issue of, rounding the corners. So again, as I said last time, you can either kind of do this explicitly and round the corners, or you can say, really what we have is we don't really have this. Your handle, it has another piece that's like this, And then you also have to kind of thicken or take the flow, kind of glue with the cylindrical part here so that you don't have so that you don't need to round the corners. But anyway, I think it's much simpler to just kind of do this brute thing, which introduces corners, and then to just smoothen the corners. Topologically, it's easier to see what's going on here. Okay? So I want to just draw one more picture here, because this handle attachment process is extremely important. It's the crux of the thing. So I want to make sure you understand. So I want to kind of draw a picture of the one-dimensional thing again, and kind of this picture that I drew there. But so kind of what happens with, let's say, the most basic handle you can think of, which is non-trivial, which is this one. So, kind of what's happening. I guess it doesn't matter this part here. I just kind of want to see what happens here. So this picture here is a picture where the dimension is 2, and I have a critical point of index 1. So I have some manifold down here which I don't really care about, but this guy here is the kind of the boundary of x I, and I want to see how do I get to my xi plus 1. Okay. So you see, really what I have here is I have this critical point of index 1. So I have to look at, basically the unstable manifold of this point. So the unstable manifold is kind of this disk here. So this is a B1. But when I look at the intersection with this, with the level set, though, so this is my AI. You see, this is a sphere. This is an S0. I guess you can think of here is the rest of your. So here's your xi, whatever it is underneath. So how do I attach this handle? Sort of the way without worrying about corners is I just choose an S0 on the boundary. Then I thicken it a little bit. So I embed an S0 times an S0 times a D1. And then I take the union with my handle. And topologically, this is what I get. And it's not hard to see that this is exactly the same as this other object. After you smoothen the corner, that's kind of the same as taking this guy. So after you smoothen the corner, then this is going to be diffeomorphic to kind of going all the way up there. Yeah, so you can either do that, or you can just kind of say this whole thing is the one handle. But in terms of diffeomorphism type, it doesn't make a difference to smoothen the corner or to just kind of attach this whole guy, this whole handle. Okay, and you can think about this like this has a local model, which as you said I'm going kind of back and forth between smoothing the corner or not smoothing the corner, but this thing the thing after you smoothen the corner also has a local model, which is kind of you have your handle like this, and then you have these little pieces. And I wrote down the formula last time. And kind of what you can do is once you have this picture, then you can actually apply the flow of V, and then you're going to get something like this. something like this, something like this, something like this. That's kind of away from the little neighborhood. And over here, you just kind of get the thing that's cylindrical. These parts here. That you just kind of attach the rest of the manifold where you're not attaching the handle times some kind of big interval. But anyway, I still think that it's simpler to just attach handles and then kind of smoothen the corners. So from a topological viewpoint, it's good enough, and it's much simpler to understand. Okay, so that's the handle attachment process. So really, the only thing you need to determine the handle attachment is this. Which, again, you can think of, up to the diffeomorphism, you can make this ball as small as you want. So really, what you really need is just an embedding of a sphere with a specific framing. So you need a submanifold of the boundary, which is diffeomorphic to a sphere, that has a chosen framing. And that will give rise to a manifold. That will give rise to a handle attachment, to a new manifold. Okay, is that clear? Are there any questions about that before I continue? Okay, so once we understand that, then we can talk about what it means to slide a handle. So what is a handle slide? And notice that for the handle attachment to really make sense, the Morse function is not enough. I need a gradient-like vector field. Because in a neighborhood of the point, basically there's nothing really going on. But when you leave the little neighborhood of the critical point, then to see how this handle attaches to the rest, you really need to see exactly where the unstable manifold falls. And that's kind of where the handle slide idea comes in. So the handle slide idea is the following thing. So you let phi t, actually, no, I'm using phi for the flow. Let's call this psi, the handle, the attachment map. Oh, and actually, let me use some names. So this sphere here, inside of xi, we usually call this the attaching sphere. So this is called the attaching sphere. Sphere. Okay. So, which this attaching sphere is by definition the intersection of the unstable manifold with the preimage of AI, this fixed regular value. Okay, that's called the attaching sphere. And often people call the other sphere. So kind of there's another sphere up here. Where's my colors? Over here, there's another sphere, which hasn't had relevance yet, but I guess I can just define it now, which is the sphere that's over here, in the local picture, but that you can move it away. So this is the intersection of the stable manifold of pi plus 1 with the following chosen regular value. And this is called the belt sphere. So this is a sphere of dimension n minus k minus 1. And this is called the belt sphere. Anyway, it's going to come, the relevance of this is you see in a little bit. But anyway, now we're only talking about the attaching sphere. So now let's say that we have a path of an isotopy of embedding. So this is an isotopy of, well, let's try like this, times b n minus k to the boundary of xi this is an isotopy of embeddings. So now you can think about the handle attachment corresponding to phi 0 and the handle attachment corresponding to phi 1, psi 0 and psi 1. So if you use psi 0, you're going to get one manifold. So you get xi plus 1, which is what you get from attaching a handle according to psi 0. And then you get, let me put a 0 here. And then you get another xi plus 1, which is the manifold you get when you use psi 1. And basically, it's not hard to see that the isotopy will actually induce a diffeomorphism here. So if you just kind of construct it explicit like this with a handle attachment, it's because of the isotopy, it's not hard to see that you get a diffeomorphism. So, the manifolds that you construct this way are diffeomorphic. But it's actually even better than that. You can see, if you see sort of the original, if you see the isotopy of embeddings as happening inside of a manifold. So this is kind of an explicit construction. So you have this isotopy of embeddings, and you kind of construct two manifolds, and they are diffeomorphic. But you can think of it from the Morse theory point of view, which is that kind of the handle attachments are not constructing the manifold, but they're just describing what's already happening inside the manifold. So kind of you already have your Morse function, and the handle attachment is just describing what's happening with a gradient-like vector field. So sort of here's your manifold xi. And then you have your critical point, pi plus 1. And basically, you have a chosen gradient-like vector field. And that, so and then you have your psi, which your psi is just kind of this map here, which looks at basically, your psi just looks at a neighborhood of the attaching sphere. So, you have your attaching sphere, which is just that thing. So your attaching sphere is just the unstable manifold intersection with this guy. And you look at a little neighborhood of this guy inside of the boundary of xi. And that gives you one specific embedding. So when you look at this little neighborhood, this will give you one embedding of sk minus 1 times bn minus k inside of the boundary of xi. Okay? And then suppose that you can find an isotopy from this phi, from this psi to something else. So suppose that there exists, an isotopy psi t such that psi 0 is equal to your psi that comes from your Morse function. So then the result is that then there exists another gradient-like vector field v tilde, so that the attaching map for v tilde is psi 1. So such that psi 1 is the embedding that corresponds to the attaching map of v tilde. Okay? So, basically, psi 1 is the embedding of this guy into the boundary of xi, corresponding to v tilde. Now, what does that mean, corresponding to v tilde? V tilde is another gradient-like vector field, so it will induce a flow. And in this flow, you can look at this, the unstable manifold with respect to this other flow. So that's going to be a different manifold. The unstable manifold doesn't depend only on the function, but it depends on the vector field. So you're going to have a different vector field, and this is going to be a different sphere. But basically, this isotopy is gonna tell you a way to go from this vector field to the other vector field. So that's kind of what the result says. And how do you do this? I mean, it's a little hard to write down all the details, and I don't really want to do that right now. But I guess one way to do it is to actually use this diffeomorphism. So kind of, I'm going back and forth between saying, I have a manifold that doesn't change, and I have a Morse function, and I want to change other stuff. So kind of clearly the diffeomorphism type is the same. And going to this perspective where you kind of are building your manifold out of the handle. Okay? So I guess, one way to do this, to prove this result, is, I can kind of draw a picture and say, say that my xi is here. And saying that I have a map, here's my attaching sphere for my original curve, for my original handle. So, I have my gradient-like vector field here. So if I and here is my, this is my v, my original v. So if I want to isotope my handle and construct a gradient-like vector field in this isotoped situation, what you can do is, how do you do that? So what you can do is first you look at a tubular neighborhood of the boundary of xi. And away from this tubular neighborhood, you keep your same gradient-like vector field. And as you perform your isotopy, you will move your vector field along this isotopy, I guess, with a bump function. So I can write this down, but maybe it's better to just draw the picture. So my original vector field, gradient vector field, it's kind of like this. And as I move the handle, say I take an isotopy that moves this point over here, then the new picture that I have is the following. So, say that I moved my handle a little further away. So inside the handle, the gradient-like vector field is going to be the same. But now my v is going to do this. Okay, so kind of you use your bump function to take your gradient-like vector field that you already had and move it along so that it kind of still glues in the original way. Okay, so that's kind of how you obtain. So basically, why do you do that? So that basically outside of this neighborhood, you don't change anything. So like on the boundary of xi plus 1, which is diffeomorphic to this boundary here, you kind of aren't doing anything because you're just kind of stretching it. Okay, so of course, this is not a rigorous proof. So you have to write down really what I mean by that. But I claim that really you can look at the isotopy and you can use a bump function to really move things along, to understand what's happening with this handle attachment. With this handle slide. So basically, the more of the story is you can slide your handle around, but by just kind of moving the attaching map, like where your attaching sphere is going, and that just corresponds to changing the gradient-like vector field, without changing the Morse function. Okay, so I guess maybe it's instructive to have an example right now. So you really see what's happening. So maybe we can go back here, actually, to this example. Yeah, so, kind of, you can really think of this example, without just thinking about the handle, kind of, this part here doesn't really matter. We don't need to draw my function where the boundary, has the value of the function is constant there, in terms of the topology of the manifold. It doesn't really matter what the Morse function is. The only thing that matters are these handle attachments. So to simplify the situation, I'm going to say, I'm just going to have my handle attached like this. Okay? And I'm just going to smoothen the corners. So this is what happens after you attach a handle. Okay. And then now, one thing you can do is, you can move your handle around. So when you slide your handle around, you don't see really any big differences topologically here. Or topologically, it's kind of easy to see I have a diffeomorphism. But what's interesting here is, like, what if I attach another handle? So if I attach another handle, then, that means, I'm kind of, say I choose my S0 here, and I attach another handle. Then I have something like this, the resulting manifold. And what is interesting to see now is that now I could actually slide this handle kind of through the previous handle. So there's nothing that prevents me from doing that, because once I go, kind of once I attach my handle, and then I have my xi plus 1 here, then I can attach my next handle wherever I want on the boundary of xi plus 1. And if I kind of still keep track of my handle down here, then what I can be doing is I can be sliding this handle along the boundary of the other handle, along the boundary that I introduced from the other handle. And here, really, the topology is not going to change. I mean, the topology doesn't change because of this fact. We get a diffeomorphism. But in this specific case, actually nothing very interesting is happening. When you take your handle and you kind of move it along here, you kind of, in this embedding, it seems like you kind of flipped, but you kind of do a whole flip. You don't really change anything about the topology, what you're seeing here. But we'll see in a little bit that when you have unoriented handles, interesting things kind of happen with these handle slides. Okay, but kind of, I think the point is, like, for the handle slides, there are two kinds of handle slides you can do. One is like a little small handle slide that doesn't really change anything, even when you look at it. But if you can do big handle slides, like handle slides don't have to be small. And if you do big handle slides, what's kind of crucial here is what happens when you do a handle slide where the attaching sphere is crossing the belt sphere from a previous handle. So like when you look at the previous handle right here, kind of, if you have two, so if you have sort of, so here is your AI, here's your AI plus 1, and here is your AI plus 2. So, you have a handle here, which I'm going to kind of think like this, and then you have another handle here, which I'm going to draw like this. And these things that I'm drawing schematically like this are the unstable and the stable manifolds. So, this is an unstable manifold of pi, and the stable manifold of pi. This is the unstable manifold of pi plus 1, and the stable manifold of pi plus 1. So what I'm trying to say is, if the stable manifold of pi and the unstable manifold of pi plus 1 don't intersect, and they don't intersect through the isotopy, then like really nothing is changing very interestingly. But what can become really interesting is when you do a handle slide here, which is going to cross the stable manifold of a previous handle. So that's when something kind of interesting could happen. And that's kind of what happens when you really move through the middle of a handle. Because like kind of going through the middle of the handle, in a way, it means that you're going through the belt sphere of this handle. I mean, of course, the belt sphere is only like really in the middle of the handle. You're like, oh, what if I just kind of go around, go for a ride, and go a little bit in and go out? But you can think of the handle as being something kind of really small. Like kind of the whole handle is just a little neighborhood of the belt sphere. So kind of if you're going to go through the handle, you kind of really almost have to intersect the belt sphere. Like, if you don't intersect the belt sphere, then you kind of go in and out. It's isotopic to not even touching the handle. So that's why, I'm kind of saying, the interesting thing really is when you kind of intersect. So through this isotopy, you go through a point where you intersect the belt sphere of the other handle. And then you can have very interesting changes. In dimension 2, you don't have kind of very crazy things. But already in dimension 3, like these handle slides can be really, really interesting. I mean, they don't change the topological, they don't change the underlying manifold, but they will change the handle attachment in significant ways. Okay? So that's kind of why handle slides are so important. And of course, you can do these little handle slides to show that, morally, it doesn't really matter exactly where you attach, but just kind of the isotopic class of the attachment. Okay, so that's kind of the first step, is understanding that you really only have to worry about, these handle attachments up to isotopy. Okay, so we haven't quite simplified very much. We just simplified a little bit. But now the next big step is trying to switch the order of the handles. So that's what I want to explain now. Are there any questions so far or about the handle slides? I think also, with examples, things can get a little clearer. So in a little bit, we're going to classify surfaces, and I guess the handle slides will come in handy. Okay, but now I want to talk about switching the order of the handles. So let me write down the proposition. So proposition. Let f be a Morse function as above, as usual. And suppose that the index, so we have two kind of adjacent critical points, but the index of pi minus 1 is bigger than or equal to the index of pi. Okay? So the goal here is to actually, maybe I should say what the goal is before. So the goal is to order the critical points in regards to their indices, to the Morse indices. So if we have a critical point that's below, so this guy has the image, the critical value is less than pi. But if the index of this guy is bigger than or equal to pi, then I can reorder. So then, then there exists, then for any a and b, if I choose any numbers in the interval from ai minus 2 to ai minus 1 to ai plus 1. So here below this I have ai minus 1, and here I have ai, and here I have ai plus 1. So if I choose any two numbers between ai minus 1 and ai plus 1, a and b, there exists another Morse function such that the critical points of f tilde are the same critical points, and such that f is equal to f tilde outside this interval, so ai minus 1, ai plus 1. Let me write this below. And f of pi minus 1 is equal to a, and f of pi is equal to b. Okay? So basically, if the index of pi minus 1 is bigger than or equal to the index of pi, then I can change my Morse function just in this interval to take pi minus 1 to whatever value I want, and pi to whatever value I want inside this interval. In particular, I can change the order of them. Okay? And make the, so kind of the goal is to do this where B is less than A. Okay, but I can actually do for whatever A and B I want. But I can, in particular, make the B less than A. In particular, we can do that for B less than A. So that means, if I happen to have a critical point with a bigger Morse index than a critical point that's above it, then I can change the order, at least if they're adjacent. If one is next to the other, I can do that. Okay? All right, so let's prove this. I guess, a sketch of the proof. So, we take V to be a gradient-like vector field. So as usual, let V be a gradient-like vector field. As usual. And let me call K the index of Pi, and L the index of Pi minus 1. So then, if we look at the attaching sphere of Pi, so here there's an attaching sphere of Pi, and there's a belt sphere of Pi minus 1. So I have to look at them. So the belt sphere of Pi, so the attaching sphere of Pi, so this is the unstable manifold of Pi intersected with AI. So this is a sphere of dimension S of dimension K minus 1. Right? And similarly, the belt sphere of Pi minus 1 intersected with this guy is a sphere of dimension n minus L minus 1. And now, up to a slight perturbation of V, we can assume that these guys intersect transversely. So up to a small perturbation of V, we may assume that these two intersect transversely. But now, because K is less than or equal to L, then there are not enough dimensions here to get to n minus 1. So intersecting transversely means that they don't intersect. Because these guys intersect transversely in the pre-image of AI. Sorry, this is not intersected with AI. It's intersected with the pre-image of AI. Okay? So this is contained in here, but this has dimension. This is a manifold of dimension n minus 1. So the maximum these guys, they don't have enough dimensions to intersect transversely unless they don't intersect. So if they intersect transversely, so that means that they don't intersect at all. Which will mean that now I can actually continue the unstable manifold And if it doesn't intersect the stable manifold of Pi at this level, then it will never intersect the stable manifold of Pi minus 1. So that means, that basically, so that means that the unstable manifold of Pi inside of this guy, all the way from AI minus 1 to AI doesn't intersect the stable manifold of Pi minus 1 intersected with this guy. Actually, they don't intersect at all, but in particular, they don't intersect inside. Let me just write it like this. So they can't intersect at all. So in particular, they don't intersect inside of this chunk. Okay? All right, so now I'm going to define the following function. So now I'm going to let HS be a family of maps. So these are going to be, so this is a family of strictly increasing functions. Smooth functions, which are going to be the identity in a small neighborhood of AI minus 1 and AI plus 1. So such that HS of x is equal to x near AI minus 1 and AI plus 1 for every s in 0, 1. And it has the following other property. So I want that H0 of FPI minus 1 is equal to A. And I want H1 of F of PI to be equal to B. So I can draw a picture, but this is kind of a real analysis problem to see that you can do this. It's pretty easy to see. If I draw a picture, I can convince you. So you kind of have AI minus 1, you have AI, and you have AI minus 1, AI plus 1, and then you have AI plus 1. So you have this closed interval. And I want an isotopy of functions that are always increasing. So in particular, they are all diffeomorphisms. I want them to be equal to the identity. And then I have, f of Pi minus 1, and then I have f of Pi. So I want for the first point of the homotopy, I want this guy to be equal to some a. So I can find a function that is going to go like this. That's strictly increasing. And then I want this to end at another function where this guy is b. So I can find a homotopy of functions that does that. Okay, of course, I might have to take these little intervals to be really small. But once I fix A and B in the interior of this interval, then I can do this. Okay? And then now I'm going to choose a bump function. But I'm going to kind of do it wisely. So now, so I'm going to let phi that goes from this f inverse of ai minus 1 ai plus 1, I'm going to define a bump function wisely. So how will I define this? Let this be defined as follows. So first, I define it to be 0. So first, I'm going to define it on the pre-image of ai minus 1. So I want to define a function, like a bump function on this whole thing here. But first I'll define it just on this slice here. So in the following way. So I will let it be equal to, I will let it be identically 0 near the unstable manifold of pi minus 1 intersected with this guy. And then I'll let it be identically 1 near the stable manifold, no, the unstable manifold of pi intersected with this guy. Okay, so if I look at the unstable manifold, this unstable manifold is going to come all the way here, and this one is going to have an unstable manifold that comes here. So I let it be 0 here, and I let it be 1 here. I mean, of course, these guys don't intersect because they're unstable manifolds of different critical points. So the flows are converging to different critical points. So they can't intersect. They can't be on two different unstable manifolds. Okay, so I can easily define it to be 0 here, to be 1 there, and I can extend the bump function on this whole hypersurface here. So I can extend psi arbitrarily to this hypersurface. And then what I do now is now what I can do is now I can use the flow of V to extend psi to this whole product, to this whole little chunk of manifold. So basically, now I can use the flow of V to extend psi to at least this pre-image of these guys, a minus 1, at least away from the unstable and the stable manifolds. So, away from this, away from the unstable manifold and the stable manifold, and the unstable manifold and the stable manifold. And then I just set it to be 0 on these parts and to be 1 in these neighborhoods, and then you're done. So okay, maybe I should draw a picture to make it clear. So so here's my manifold. Here's pi minus 1, and here's pi. So I have an unstable manifold. I know the two different unstable manifolds never cross. But in principle, the stable manifolds could cross. But because of my assumption of transversality, I know that these stable manifolds never cross. So basically, when I look at the unstable manifold of pi in union with the stable manifold of pi, and I can even look at a little neighborhood of it, this will not intersect the unstable manifold of pi minus 1 union the stable manifold of pi minus 1. So these two manifolds don't intersect. And if you thicken them a little bit, they still won't intersect. So that's why you can define psi to be basically 1 here and psi to be 0 here. And you can basically choose these neighborhoods so that, along, I can kind of try to draw it like this, So you choose the neighborhood so that the flow of your vector field is tangent to the boundary of this neighborhood. So you can just kind of you can just choose the neighborhood like that. So like along, if you flow your vector field, you're kind of along the boundary of this neighborhood. And you can do that for pi minus 1 and for pi. Okay? I mean, another way to do that is just kind of, you just fix this neighbor, you take a small neighborhood of this unstable manifold of pi minus 1 intersected with this guy, I minus 1. This is a sphere. So when you look at a small neighborhood of it, then you get, kind of, you get this other sphere of a different dimension. And when you flow this manifold, you know that it cannot be trapped by pi. It's like when you flow it up, you can't be trapped by pi. And that's because of the transversality. So it has to go all the way up to the other level. It can't stop. It can't stop at this critical point. It has to keep going all the way to a plus 1. So basically that's kind of outside of this range. You can extend psi just using the flow so that it's constant along these flow lines of v. So that's kind of how you do it. So let me say it one more time. How do you define this bump function? So you define it to be 0 on the unstable manifold of pi minus 1, and 1 on the unstable manifold of pi, and in a little neighborhood of them. And then outside of these neighborhoods, you can flow and you actually get a diffeomorphism from this level all the way to all levels, all the way to the top. So just using the flow, you define the psi to be constant along these flow lines. Okay? And then what's not in these flow lines is it has to be a neighborhood of the stable and the unstable manifolds of pi minus 1 and pi. Those are the only things that don't flow from here to here. Those are the only things that get trapped inside. And like inside of these neighborhoods, you're either kind of near a stable manifold or unstable manifold of pi minus 1 or of pi. And then you define one to be psi equals 0 and the other one to be psi equals 1. And everything's smooth almost by construction. So anyway, you get this bump function. Okay? So once you have this bump function psi, then you can define your new Morse function to be simply so now you define your new Morse function f tilde of x to be h psi of x of f of x. If x is in ai minus 1, ai plus 1, and just f of x otherwise. Okay, so kind of basically within this neighborhood, you kind of lifted this value up to your a. In this other neighborhood here, sorry, this yellow line doesn't make any sense. The yellow line is supposed to go up. Yeah. So in this other neighborhood of this pi, you kind of change the value of this guy to be wherever you want. And you're doing it like in a family. So this is kind of all, this is all well defined because this hs for every s is a strictly increasing smooth function. So anyway, this will be a new Morse function. And you have to check really that, it's not hard to see that you will have this property. I mean, that for the new Morse function, the value, that pi and pi minus 1 are still critical values, critical points, that's easy. And that their images are a and b is also easy. I guess the only tricky thing is to see that you didn't create any new critical points. And that's a little subtle. But that's true because of the way that you chose your bump function. Because you chose your bump function to kind of be constant along these flow lines. So this is kind of the point of the proof that you need to write down, is to see that you don't, so I guess exercise is to check that the set of critical points doesn't have any new critical points. So this is equal to the set of critical points of F. It's not completely obvious, but it's true. Okay, any questions about this? So the corollary of this proposition is that if X is a closed, is a compact manifold, then there exists a Morse function F with critical points P1 through Pm, where f of P1 is less than f of P2, etc., less of Pm, and the indices are in increasing order, like that. Or in non-decreasing order. Okay? Because every time it doesn't happen, then you can change the order by this proposition. Okay? So that's what we get. Okay. Any questions about this? Is that clear? Mm-hmm. Uh-huh. Não, ela é estritamente crescente. É só isso que você precisa. Oi? Não, mas ela não vai ser estritamente crescente. Estritamente crescente. Okay, maybe what I mean is by strictly increasing is the derivative is always positive. So maybe that's HS prime is always positive. You can always do that. Beleza? Okay, so that's the first thing. So this is kind of very nice because in principle, we don't know about the order of attaching handles. Like you could start, in low dimension it's not so hard, but in higher dimensions you could think, first they attach handles of index 1, then 3, then 2, then 4, and it could get really messy. But this thing is telling you actually you can do everything in order. And actually, if you just kind of tweak this argument a little bit, it's not so hard to see that basically because one other corollary from this proposition is because we really needed the index to be greater than or equal to this one. So if these have the same index, then you can change them around too. So even with equality, you can change the order. Or if you want, you can do them all at the same time. So this is not the condition that I usually say, I want one critical point for each critical value, but maybe you might say, actually, I want to do all of them at the same time, like all of the index 1 critical points at the same time. So you can kind of think that all the handle attachments of the same index are independent. So you're not attaching a one handle to a previous one handle. So you can assume that all the one handles are attached separately, in separate parts of what comes below, and so on and so forth. Okay? So sometimes people talk about like a self-indexing Morse function, which is sort of like where this happens. So instead of having one critical point for each critical value, you say, for the critical value, say 1, that's where you have all the index 1 critical points. For the critical value 2, you have all the index 2 critical points. So you kind of attach all of the index k critical points at the critical value k. So sometimes people do say that. But it kind of depends on the context and what you're trying to do. So it's better to understand than to just kind of memorize the statement of the result. Okay, so any questions about this? So this is kind of or switching the order of handles. And the next step is canceling handles, and the kind of this very beautiful part. Okay, let's do that. Oi. Olha, faz a conta. Você tem que fazer a conta e fazer a conta da derivada, né? Vai ter uma regra da cadeia aqui, né? Isso tem a ver com o fato de que o H, o psi, ele é invariante na direção do dv, né? Na direção do gradiente da função. Então você vai conseguir mostrar que nessa direção a derivada continua sendo diferente de zero, então não pode ser um ponto crítico. Yeah, so. All right, so now let's talk about handle canceling. Handle cancellation. This is probably one of the most beautiful results. So it says the following. Theorem. Suppose that, I have the same setup as before. Suppose that the index of pi is equal to the index of pi minus 1 plus 1. So take two consecutive ones where the difference of the index is exactly 1. And such that W of pi intersects Ws of pi minus 1 transversely, and this intersection at the level F inverse of AI is a single point. Okay, if they intersect transversely, this will be a zero manifold, but we want to suppose that it's a unique point. Then there exists a Morse function f tilde such that f tilde is equal to f on outside of this interval, so on outside f inverse of ai minus 1, ai plus 1, and f tilde does not have critical points in this interval. So that means that we can actually cancel out these two critical points. Or in other words, we can cancel out these handles. And we're going to obtain a new function that doesn't have any critical points in this interval, or there are no critical values in this interval. So topologically, this is trivial. So that's the idea that you have two handles that cancel out. And the condition that you need is this one. So you need the unstable manifold of pi and the stable manifold of pi minus 1 to intersect exactly there exists a unique flow line, or if you take any slice, there's a unique point. And that's what you need to be able to cancel them. Okay, so how do we prove this? And again, I'm not going to prove the whole proof. You have to look at some other book for this, maybe Milner. So, you can look at, so for more details on this stuff, you can look at details. You can look at Milner lectures on the H-cobordism theorem. But let me do a sketch of the proof. So what's the sketch of the proof? So I have my PI, and I have my PI minus 1, and I have my flow line from PI to PI, from PI minus 1 to PI. So, because I have a point over here, if I take this point, I can flow it all the way down to PI, and I can flow it all the way down to PI minus 1, and I can flow it all the way up to PI. Maybe, I can draw it like this. So here's my PI, here's my PI minus 1, and then I have a flow line like this. Okay? So, basically now I can have this guy, it will have, I can write it like this, and then this guy has a direction like this. And, So now is the step that I kind of won't say very much, but there exists a chart near this flow line. So there exists a chart in a neighborhood of this flow line. So the flow line is the intersection of the unstable manifold of PI with the stable manifold of PI minus 1, such that the vector field V has the following expression. So I can think of this, actually, so I want to, so such that, so say phi, so there's a chart phi from U to Rn such that psi of Pi minus 1 is equal to the origin, and say phi of Pi is equal to, I'm going to write it like this. So 0 and then 1, 0. And this guy is the kth factor. And my vector field, and such that my vector field, x1 through x, so the index, I want the index of Pi minus 1 to be equal to k. So then I want my vector field v of x1 to xn, so it's going to be minus x1, and then for xk, it's going to change signs. So, there's going to be some function sigma of sigma of xk. No, sorry, I want my vector field to be, oh, that's right, yeah. I guess I can write it like this. So minus x1 ddx1 minus etc. And then I have, so for xk, ddxk, I have some sigma of xk. And then I have plus xk plus 1 ddxk plus 1 plus etc. plus xn ddxn. Okay. So this this sigma, I'm just going to write it here because it's closer. Yeah, sorry, I'm erasing the theorem. I think I actually want the index of pi to be k. And the index of pi minus 1 is k minus 1. So I can choose this kind of, if you stare at this picture, you can actually find a local form for this where the sigma k, the sigma of xk is a function that is equal to xk near 0 and is equal to 1 minus xk near 1. So that's the function that you want. So sort of something like this. So it's here is 0, here's 1. Here's your xk, and here's sigma. Okay? So that's not completely obvious that you can do, but basically, kind of using your gradient-like vector field in the neighborhood of a gradient flow line from 2 points like that. Basically you can do it so that in every other direction the vector field is constant, just equal to you have the directions going out and the directions going in. I mean here it's kind of just in this picture I just kind of want it to be like this, or at least this component. Or the x2 component here, it's kind of constant equal to x2. And then in this picture, actually, sorry, here's the x1 component that's kind of always equal to going out. And maybe to be consistent with this picture, I actually want to be in. Whatever. Doesn't matter. So I want so in my picture, I have the x1 component, which is always minus x1. And for x2, I have something that starts, with x2. And then when you get close to 0, 1, then it becomes 1 minus x2. So there we go. So it's something that has 2 zeros, from here to here. And it goes up and then down. And then after that, it's kind of pointing down. So it's kind of negative here, and it's negative here, as you can see, if you try to continue this guy. So this is kind of like a neighborhood lemma. And Milner has a nice proof of this. But I guess it's not too hard to believe you can do this. By just kind of using this one particular gradient flow line and integrating it in a nice way, you can get this behavior. So once you do it in this behavior, once you have this behavior, then it's not hard to see that you can change this vector field to a vector field that doesn't have any zeros anymore. So now you can just kind of take the sigma, and you can homotope it so that it just kind of goes like this. So now we can change V to a non-vanishing vector field, V tilde, which coincides with V away from, or outside this neighborhood. Outside this U. So you kind of, you have what you had before, and then inside you just modify it so that now it doesn't have any zeros. So in this picture, what we can do is, if you have this, you can replace this by, the following vector field just goes like this. And then it goes like this, and it goes like this, Which is exactly what you get if you replace the sigma by another function sigma that doesn't have any zeros. That's just that's just always negative in this picture. Okay? So so now we replace V by a V tilde. But we're not quite done, because we can do that anytime you have a flow line. It doesn't have to be the unique flow line. You can always kind of do that for anytime you have a flow line connecting 2 points where the difference of the index is 1, which is a crucial point, you can do this modification. But now, really, we have to use, and sort of now I'm going kind of from Well, let me go here. So let me draw the picture so you can see really what's happening. So, so now I have my, so here's AI minus 1, here's AI plus 1, and then here was my PI, and here was my PI minus 1, and I have this flow line connecting them. And what I'm doing now is I take this neighborhood, and then I am replacing this vector field by another vector field that does what? So it kind of, basically it's non-zero here. So, it enters this neighborhood, and then it leaves this neighborhood. So it enters this neighborhood, and then it leaves. So instead of being trapped by these guys, it kind of enters and leaves. And now I really need the fact that this is the unique flow line connecting these two. Because that means that if I have if this vector field, so sorry, let me write this. So the stable manifold here just intersects the unstable manifold here, which means that if I leave this neighborhood, if I leave PI, I will not re-enter here. So when I leave this neighborhood, then the only thing I can do is flow all the way up here. I mean, of course, the stable manifold, the stable manifold here doesn't come back down. But there would be a risk if you have another flow line connecting PI with PI minus 1 with PI, there would be a risk that it would come back to this point. But we're assuming that this is the only flow line. So that means that when I leave this guy, I have to flow all the way up, and I don't get trapped by this neighborhood again. So that means that if I have a flow line that goes and then enters here, then for this v tilde, it can be, it can go all the way down and come out like somewhere here. But then it will not flow back up, it won't flow back into this neighborhood. It will just keep going out over here. So what this means is that for this v tilde, so every flow line of v tilde goes from f inverse of ai minus 1 until f inverse of ai plus 1. And here, again, that's where you really need that there's only one flow line connecting pi minus 1 to pi plus 1. Okay, so the only way to get from pi minus 1 to pi plus 1 is on this unique line right here. Which means that if you leave the unstable manifold of pi minus 1, there is no way you can come back here, even for v tilde, because I'm not changing v tilde away from this neighborhood. So this is really what you need. So what we show with this construction is that you can find a vector field that never vanishes, that's non-zero, in this neighborhood. So that actually already proves that this neighborhood is a product. So this already proves that this set here, the pre-image of ai minus 1 to ai plus 1, is a product of f inverse of ai with an interval. Because you can just look at the flow of v tilde normalized. But now if you just look at v tilde normalized, and you kind of integrate that also gives you a new Morse function. So that, if you look at kind of v tilde normalized, that will give you a new Morse function on this whole thing that goes from ai minus 1 to ai plus 1. So this will, kind of, if you just flow along v tilde and you have to to do some kind of normalization, it's kind of a subtle thing, but then you actually obtain this f tilde, this new Morse function, which doesn't have any critical points in here. Okay, but I guess it's important to see that the key element here is that there's a unique flow line. Otherwise, you would have loops, and then there is no way to do this. Then you can't, because the idea is the function has to increase along the flow line. But if you have a loop, then you're screwed. It doesn't work. So for example, if you, I guess the most simple example you can think about is if you look at the circle, or I guess a non-example. So you see that you can't cancel everything, but like a non-example is what happens if you just look at a circle. So you have these flow lines. So this is a circle with two critical points, and you have these flow lines. So you can, look at a neighborhood of this guy, this neighborhood. And actually, you can find, so if this is your original V, then you can find a V tilde that doesn't have a 0. You kind of just replace this guy with, so inside this neighborhood, you replace this with this guy here. But the problem is you used to have another connecting line from here to here. So that means, okay, here you're fine, but then you still have this line here. So that's why it's bad. Like you can't cancel this because now you can't define a Morse function anymore. Like in this interval here, that it just doesn't work. That construction doesn't work. Okay, but maybe this picture doesn't have enough dimensions for you to understand what's going on. Yeah. Se o índice for... Funciona. Deixa eu dar mais let me give you another non-example. Maybe it's a little easier to see the problem. Like if you take a torus, for example. Well, let's say, you just build one handle and one zero handle like this. Okay? So you have this critical point, and you have this critical point. So I'm going to give another non-example, and then I'll give you a real example of a cancellation. But I think the non-examples are good. Well, let me give you let's start with the example, and then the non-example. So here's an example. Okay, so take this index 1 critical point, and take this index 0. So you see that here you have a unique flow line from here to here. And I have a level here, and I have a level here. So sort of this was the AI minus 1, and this was the AI plus 1. So you have a unique flow line here. So that means, in a neighborhood, I can find a vector field that's non-zero. But now my vector field, it flows like this. So I enter here. Sorry, my flow line is flowing up. But now, my gradient-like vector field kind of comes here, and then it goes down and comes out here. But that's okay, because I have this is the unique flow line connecting these 2 points. So if I come here and I flow down here, then when I get out, I still am going to flow all the way up to here. So this will allow me to extend this vector field to really a non-vanishing vector field where the flow will take every point here to a point up here. And I can use this flow to define a new Morse function. So you really see that these two are canceling. But anyway, here's a non-example. So if you were here, then you actually have 2 flow lines. And again, what's the problem here? It's similar to the circle. Now I have an extra dimension. But if I look at, a neighborhood of this guy, the problem is in this neighborhood, I have exactly that picture there. I have, I'm going like this, out like this, out like this. So I look really happy in principle. I can cancel this and get a non-zero vector field, a non-vanishing vector field, by just, erasing this, and now I go like that. Now I'm actually leaving. But the problem is, kind of this trajectory that goes right through the middle. It enters this line, and it exits, but then it enters it again. So that means, there's no way, if I take some flow line that, so something that yeah, a direction that's yeah, but basically, you know, if I take this line, it's just going to keep coming in and out, coming in and out. So it's not going to go from the bottom, whatever you have underneath, which is here, is nothing, to what you have above. So you won't really have a flow that goes from, that takes, you know, something here to something up here, and that crosses every regular value exactly once. Or, you know, actually that doesn't make sense at first. Like basically, what the property about the v tilde that you need is that every point in the interior here, if you flow backwards, you get down to this level, ai minus 1, and if you flow forwards, you get up to ai plus 1. That's the property you need. And for that to work, you really need this property that when you look at the unstable manifold of the critical point pi minus 1, the only way that it gets strapped inside here is by this unique flow line. Every other point that leaves this guy in every other direction is going to go all the way up to ai plus 1. And the same thing with the unstable manifold of pi. So that's why you need this unique flow line. Okay? So anyway, I have an example and a non-example. And actually, okay, a corollary of this construction, which is, you know, actually extremely nice, is the following thing. So corollary is, so suppose X is compact and connected, then there exists a Morse function with a unique index 0 critical point. So if the manifold is connected, then you only need one index 0 critical point. You only need one zero handle. And that's it. You don't need any more than that. Okay, and why is that? So suppose that I have, you know, I guess this we can prove. So suppose that you have several index 0 critical points. So that means that in the handle attachment, you have a bunch of 0 handles. And because we know that we can order the handles by index, we can just kind of first we'll have all the 0 handles. So all the 0 handles will be a bunch of balls that don't connect to anything. Okay? And now we can look at the 1 handle. So maybe you say, oh, there are no 1 handles, you know, like maybe there are just 2 handles. But what happens is the attaching sphere of a 2 handle and higher up will be, so if you look at a K handle, the attaching sphere is an SK minus 1. So basically, the only way to connect these disconnected parts is with 1 handles. If I attach higher handles, then they'll just kind of be within the same connected component. They won't change the number of connected components. Attaching a higher handle won't change the number of connected components. Which means if the manifold is connected, then I have to have 1 handles connecting these guys. That's the only way. I mean, I could also have, you know, 1 handles like this. But the point is, if this manifold is connected, then there will be, you know, at least one handle where your S0 is on 2 different spheres. So if I have one such 1 handle, so if I have a 1 handle that, you know, where the attaching sphere is an S0 on 2 different spheres, then that means that, you know, one of the points of S0 is in 1 sphere, and the other one is somewhere else. It's on another sphere. So then here I can actually cancel. So if the 1 handle, you know, is an S0, so 2 points, and only 1 point is on 1 sphere, and the other point is somewhere else, that means that I can actually cancel this 1 handle with this 0 handle, because I have a unique flow line. and then I cancel this, and then so on and so forth. So I can cancel all of them, except for the last one, So as long as I have a one handle where the 2 points of S0 are in two different spheres, then I can cancel the one handle with the zero handle. And then I end up with a situation where I just have one zero handle, and potentially I have other one handles there, but the S0s are going to be on the same sphere. Okay? So that's the proof. So you can always assume that you have a unique zero handle, or a unique index zero critical point. And if the manifold doesn't have boundary, then you can flip the manifold upside down, and you can do the same thing for the n handles. So if the manifold is closed, so if the boundary of X is empty, we can also assume that there is a unique index n critical point. So now you see that we've really simplified the process. So if you start with a manifold that's closed, meaning compact and no boundary, then that means, how do we build the manifold? We start with a zero handle, with just one zero handle. Then we have to, some big mess of one handles, two handles, et cetera, et cetera. And then you end with a closing ball, which is an n handle. And you're done. So any connected compact manifold without boundary can be built like this. And if the manifold has boundary, then you don't need the n handle. Okay, so anyway, so this is the situation. And what can we do with this? We don't have a lot of time, but I think I can talk about surfaces. I can explain the classification of surfaces now that we know how to simplify everything like this. So how do we classify surfaces now? So every surface can be built, every compact surface can be built with attaching handles like this. So you start with a zero handle, which is just a disk. And then now you have to start adding handles to this, just adding one handles. And as long as if you have a circle on the boundary, you can always close it up with a two handle and be done. So you can start with this guy, and you can close it up with a two handle, and you're done. And that's a sphere. Okay? And then what can you do now? Now, on actually any little piece of the boundary, we can add a handle there. And there are two ways to add a handle, like I explained last time, up to isotopy. One is kind of an oriented way, and one is a non-oriented way. Just meaning, if I take these 2 points, which are close by, if I orient this guy like this, and I put a handle like that, then I can still orient the surface, at least locally. So like locally, this guy is still orientable. Or I can put something non-orientable that's going to mess up the orientation, like this. And then, then this is a Möbius band. But the thing is, it's a Möbius band, but the boundary is still a circle. So with the Möbius band, I can close it up and have an RP2. So if I just want one handle, if I just want one handle, and I want to close it up, the only way is to do this and to get an RP2. So it's to get an RP2. And by the way, I don't know if you thought about how to, why the Möbius band plus a disk is an RP2, but there is a very simple way to see it, which is, if you take your RP2, I drew the picture. It's very simple. If you just take the neighborhood in the right place. So if you take this point here, and you take a little neighborhood of it. It's a little ball, like this. And then you remove this ball. Then so this point, gets identified with this point, and this point gets identified with this point. So now if you remove this little ball, then what you have is this. And that's a Möbius band, obviously. Okay? So that means that, if you take your Möbius band and you add a ball, a little disk along the boundary, then you have an RP2. Okay. So anyway, but now, now you have to think about possibilities. So, what you could do is you could start adding Möbius bands. Like, you can start adding these, like, twisted bands all around. So then you would get, like, non-orientable surfaces with more and more one handles. So you could do that. So, if you add one handle like this, and then you add another kind of non-orientable one handle, you're going to get, a sequence of manifolds, which are actually going to be connected sums of RP2s. So I guess it's easier to think about these non-orientable surfaces. So, you have, with one handle, you have an RP2, and then with two one handles, you have RP2 connected sum with RP2, and so on. So you're just, every time you add another one, you're just taking a connected sum with another RP2. Because you're just like removing a ball of one and a ball of other, and that's exactly what you're doing by gluing another non-orientable handle, like this. Okay. And when I mean non-orientable handle, I mean you take a little interval of the boundary, and you put your S0 in there, and then there's a notion of orientable and non-orientable. Because in that little neighborhood, it just means like in that little neighborhood, the surface that you obtain is orientable or not. And that doesn't depend on the rest of the manifold. Of course, if I already have something that makes it non-orientable, if I already have a loop that's non-orientable, then no matter what I put, it's still going to be non-orientable. So I guess, the question is, what about orientable things? And then for orientable things, okay, so for non-orientable things, you can do this. And now let's just do orientable handles, and then we'll make them interact and see what happens. So if you just do orientable things, then you choose your S0, and we can start with S0 that's close by. And there's only one thing that you can do, which is you can put a handle like this. And when you do that, you split your sphere in two. You split your circle in two on the boundary. Okay, so you end up, with something like this. And then, if you put a two handle, you kind of close it up, and this is actually a canceling handle. So you don't want to do that. So what you can do is you can keep growing the number of connected components. So you can put another S0 on the same connected component, and then you're going to kind of split it up, and split it up, and split it up, and split it up. And then, or what you can do is you can actually choose an S0 on the same connected component. On different connected components. And when you do that, then you connect your surface like that. And what you obtain really is like what the picture that I drew last time is something like this. So basically, it's kind of a combinatorial exercise now to kind of study all these possibilities and to see that really, up to isotopy, it doesn't matter like if you split up your circle several times and then you use S0s to reconnect them several times, that's the same as like splitting up and connecting, splitting up and connecting, splitting up and connecting. Not with a two handle, but just with one handles. So it has to do with like how these S0s are intertwined. Okay, these S0s where you're doing this handle attachment are intertwined. So they have to be intertwined for the manifold to be connected afterwards. Okay, so that's kind of what happens. So if you just do orientable things, it's not so hard to see that really the only thing you can obtain is this genus G surface that we're used to. So basically if you attach 2G orientable handles, one handles, this, in the right way, we can attach these to a zero handle. And if you attach these in a way that's intertwined, you'll get something that has a unique, just one connected component at the top, and you can close it up with 1-2 handle. And then you get your 2G, your 2G, sorry, genus G surface. So this is the genus G surface. And you need twice as many one handles. Okay, so that's okay. So that's like the orientable world. This is kind of the very obviously non-orientable world. And I guess the question that's, I think, interesting is what happens if you start to if they start to interact. So, you know, what happens if I start with a Möbius band and then I add sort of an orientable handle. So, you know, if I have my original zero handle, and then I put my, you know, I'm gonna draw it like this. So I have my Möbius band. So, you know, I'm attaching this guy like this. So this is my non-orientable handle. And then I put an orientable handle here. Okay, so what happens here? Well, you know, if I forget about whatever I attached, I had a circle. You know, the boundary of the thing was a circle. So, you know, so I started with my zero handle, and then I put, you know, some Möbius band here. You know, some one handle, non-orientable handle, but the byproduct is just a circle. So when I put a orientable handle like this, then I kind of split it up into two. So what I can do is I can kind of isolate this guy and do the same thing for the orientable cases that I do here. So basically, you know, what I really need to do is like I have to attach another handle, another one handle like this to connect to really get back to a circle. I mean, I could keep expanding, but then, you know, like then I would have to kind of go back to get a circle to be able to close it up at the end anyway. So I might as well do the, you know, after the combinatorial exercise that I explained, you can kind of open up and then close up. So you can think that your orientable handles, they come in pairs. So, you know, kind of to really get something that has a circle at the end, what you really need is you need a pair of intertwined one handles. Which means, you know, I have a one handle like this. I have another one handle like this. I have a one handle like this. And then I have another one handle like this. So this is really the interesting case. You know, so you need to attach you need to attach these one handles that are intertwined. Okay, like that. Okay, so this is something that will now have a disk at the end that you can put to close up. And the question is, what is this object? Well, you know, it's not hard to see that this is actually an RP2 connected sum with a torus. Because, you know, this is sort of, I have my, you know, non-orientable handle, and then I have my thing that's like this, and then I close it up. So, you know, this is an RP2 connected sum with a torus. So, you know, I take a torus and an RP2, I remove a disk, and I glue them. Okay, that's not so hard to see. But the thing that's interesting to see here is actually what happens when I start to do handle slides. So I'm sorry I'm going a little over, but I'll be done very soon. I want to finish the thought. So what happens is, let's now do some handle slides. Let's see what happens when I take this handle and then I start like moving it along. So I can take this handle, I can move it along this one here, I can move it along this non-orientable handle. So, you know, the way I think about this, you know, is like I take this guy, and then it enters here, and then it comes out here, and then I go over here, and then it enters here, and it comes out here. So I can actually take this part here, and I can slide it through this handle. And then when it comes out, it's going to come out yeah, it's going to come out. So if this guy is going to come out, So it's going to be a yellow one, and it's going to come out. So the back entered first, so it's going to come out with this guy was like this. The back entered first, so the back's going to come out last, so it's going to come out like this. No, the other way. Sorry, this is... Anyway, sorry, I don't have time. I don't want to go much later. But anyway, what happens is after you do a few handle slides, and maybe we can do the picture better next week, but what happens is after you do a few handle slides, it turns out that after some handle slides, this is going to be the same as attaching 3 handles in a non-oriented way that are separate. Maybe I can do this picture in the afternoon with you online. So anyway, this is going to be the same up to some handle slides of 3 unorientable handles after handle slides. What this means is that if you do RP2 direct connected sum with T2, that's the same as doing RP2 3 times. And the first one, as I already said, is a Klein bottle. So now, what does that mean? That means that you can construct all surfaces by just taking connected sums of RP2s and tori. So the genus G surface is just the connected sum of G tori. And I can also take a bunch of connected sums of RP2s. But the point is, once I have at least 3 RP2s, I can substitute 2 of them by a torus. So really, I only need to take connected sums of tori and RP2s, but up to 2 RP2s. I don't need to go any more than 2 RP2s. Okay? So anyway, that's it for now. Maybe in the afternoon, I'm going to go online on Google Meet to meet with all the external students on YouTube. And if you want, I can do this handle slide for you on the tablet. Okay? Or you can do it by yourselves, but I'm happy to finish this thought. Okay, so let's have lunch now. Okay.